So far we have seen both the theoretical way of estimating the adaptive filter coefficients and also a practical way of getting the adaptive filter coefficients. The theoretical way happens to be the normal or the Wiener-Hopf equation, RW equal to P, where R was the autocorrelation matrix of the input to the filter, W were the adaptive filter coefficients, and P was the cross correlation between the input to the filter and the desired response. We found out that using RW equal to P might be problematic if the filter order is very high. And also inverting the matrices becomes not an easy task. So an alternate solution, which is easily implementable in real world systems, is the least mean squares algorithm, or LMS, where we would determine the filter coefficients W in a more adaptive way. So we will consider a toy example here, a simple mathematical example to go over the concepts that we have seen. And in this thing, we are making a lot of very simplistic assumption, is that we assume the input to the filter would be S of n, and that input to the adaptive filter has the signal of interest X plus G, where G is a white noise. And white noise, by definition, has the mean to be 0, and the second order variable, the variance, to be 0.2 in this case. So white noise is something that has a mean 0 and a variance. So we assume the variance to be 0.2. Okay, that's a way to describe white noise. Signal of interest is Xn. So the intention is to design a second order filter. Second order indicates that there would be two filter coefficients, W1 and W2, that we need to determine. And the other input to the adaptive system during the training stage or the learning stage is a desired response. Here, the desired response is Dn, which happens to be the signal itself delayed by 2 units. Okay, so that's the desired response that's entering the filter. Now, the idea is to find the adaptive filter coefficients W. So looking into the expression RW equal to P, it's specifically here the input is S. So we make it RS W equal to P, which is the normal equation for the given example. And RS is the autocorrelation matrix of the signal that's entering the adaptive system, is basically a autocorrelation of the signal X plus the autocorrelation of the white noise. Okay, so it's essentially Rx plus Rg is your Rs. Okay, but what happens with the autocorrelation of the white noise is that it has a very interesting property that the autocorrelation of white noise is basically only the main diagonal element. So in other words, Rg will be the variance times the identity matrix, which is in this case a second order identity matrix because it's a 2x2 filter that we are looking into. So it's nothing but the variance times 1, 0, 0, 1, and we only have the main diagonal elements. And it turns out that Rg in the specific case would be 0.2, 0, 0.2. So it will only have the main diagonal elements because white noise, even if you shift by one sample, it becomes uncorrelated with itself. Okay, so just as autocorrelation with no lag, so signal multiplied by itself, it happens to be that quantity is also variance. Okay, so essentially the autocorrelation of the input to the filter S is nothing but the autocorrelation of X plus the autocorrelation of white noise, and it simplifies to the variance times identity matrix. Now, the next step, key step, is to determine Rx, and Rx is the autocorrelation of the signal of interest. And it turns out that we have Rxx0, Rxx1, Rxx minus 1, Rxx0, and you know that autocorrelation of any signal is symmetrical around the lag k equal to 0. So because Rxx k is equal to Rxx minus k, we can easily put Rxx minus 1 to be 1 as well. So just to recap, this is Rxx minus k for autocorrelation sequences. So this R matrix is as shown there. The main diagonals are RXX zeros, and the subdiagonal elements are considering the lag values in the parenthesis. Okay. Now the next step is to get the cross correlation p value going. The cross correlation p is the cross correlation between the desired response and the signal that's entering the filter, in this case S. So RDS 0 and RDS 1 is what we are looking at. Interestingly, it happens that your desired response being the signal itself delayed by 2 units, no matter what, it is uncorrelated with white noise. Okay, so as well we could do RDS as RDX as shown here, and RDX 0 and RDX 1 is what's the cross correlation matrix would be. The first sample of D is nothing but xn minus 2 times xn, so it essentially gives you the autocorrelation itself, but RXX2 and RXX3. So that's the P matrix. So this is the P matrix, RXX2, RXX3. This is autocorrelation matrix that we have. So it essentially all we need is these two matrices, then you can get the W, and it happens to be here a second order filter, so it's also easy to invert your R matrix. Now the next step is to just populate those matrices with the values. So essentially we need to find RXX0, RXX1, RXX2, and RXX3. Okay, so once we have those 4 values, we will have the 2 matrices determined for us. So just going through the simple mathematical calculation, we were given the signal, discrete sequence of the signal xn to be this, and with n equal to 0, x of 0 is equal to 1, x of 1 is 0.5, and so forth. So RXX0 is basically signal multiplied with itself with no delay, and it happens RXX0 is 1.3. In the next instant, obviously we're shifting this second sequence by 1 unit, and that's what we do the autocorrelation computation. And when we shift to the right by 1, then we get RXX1 to be 0.42. You could also shift to left, and that's RXX minus 1, and the value would be the same, okay, because of the thing that we just talked, that it is symmetrical around the origin. Now RXX2, similar way, we shift it by 2 units, and we get it to be negative 0.25. As we keep going, we need to also determine RXX3. This should be RXX3. Shifted by 3 units, and you get negative 0.1. So this is a very simple example. We just took 4 samples of the signal X and computed these autocorrelation values, and now we have to just put them in the matrices that we had. So the matrices we talked about, this is the R matrix, which was made up of RXX plus the variance. If you go back to what we started with, okay, so this RS matrix essentially is RXX plus the RG, which is nothing but the autocorrelation of the white noise. By using that thing, we have determined that the RS, that the input to the adaptive system is this matrix times the weight vector times the cross correlation matrix P. Now it becomes very simple. The weight vectors are nothing but the inverse of the autocorrelation matrix times the P matrix. Now you can compute your weight vectors W0 and W1, and there you go. Now we have designed an adaptive filter which basically uses the concept of autocorrelation, cross correlation in finding out for the given order. In this case, it happens to be order 2. So W0 and W1 are your filter coefficients. So this is one simple example of designing an adaptive filter, which is very different than how we designed fixed digital filters that we have seen before. No need to think about any transformations here, no need to look into Laplace, Z, or even Fourier. All we need to have an idea is here, an idea about the correlation values between the input and also with the desired response. Then you can easily come out with these calculations and find out. And as indicated, if the order is very high, we cannot do this numerically, and there might be also stability issues because R inverse tends to be floating point numbers, and it might get truncated in certain implementations. So a practical way to go about is using the least mean squares algorithm. Okay. So with that example, we will look into couple of key applications of adaptive filters. The many applications of adaptive filters, because it's realizable in practice. We can compute filter coefficients in real time. So the examples we are seeing could be expanded to any other domain. Now, the very first application that we are going to look into is adaptive noise cancellation or adaptive filtering in general. And here, the motivation is to basically reduce or remove overlapping interferences. Very typical in biomedical is overlapping interferences. We have an idea how to remove things which are non-overlapping, like even if you have a motion artifact, a random noise, the power line interference, we have some idea to remove that using notch filters, band stop filters, band pass filters, low pass and high pass filters. And we also have some idea about the frequency that needs to be removed there. But in many applications, when the systems are complex and coupled systems, then you have fixed filtering may not be appropriate. So we need to find adaptive schemes. And one good example is this particular adaptive noise cancellation, in which the mother's ECG would be removed from the fetal ECG to monitor the heart rate in real time, okay, when the baby is in the mother's tummy. So the configuration of this filtering technique would look like this. So the input to the filters are two things, as we have seen in before. One is normally we call the input to the adaptive filter and the desired response. Now, you got to keep that in mind, the whole concept of what is the requirement between the desired response and the input to the filter. And we use that in a very intelligent way to design this adaptive noise cancellation problem here. So all we are doing is that the two inputs we had before now are going to be looked into more carefully. So I would be sending the ECG that's obtained from the mother's chest, okay? Mother's chest ECG is M of N, and the ECG from the mother's abdomen, ECG, which is going to be A. Okay, so that's the key here. Okay, so you got to keep sure here the role of the desired response we have seen before is played by the abdominal ECG AN, and the inputs to the adaptive filter which we have seen before is played by the mother's chest ECG. So the input to these adaptive systems are a very key component, because if you flip things, then you might be looking at the wrong output. Okay, so that's the determination here. Now, obviously, the mother's abdominal ECG has two parts added. One is F, this is the fetal ECG as detected at the abdomen of the mom. Okay, the fetal ECG FN as detect the abdomen of the mom in a totally non-invasive way. And we also have another signal P added at the mother's abdomen. This P is what's causing the interference. So typically, if you just put an ECG sensor at the mother's abdomen, you're not necessarily getting the fetal ECG F alone. The mother's ECG, which is basically very dominant at the chest, which is M of N, has some kind of an attenuation, but that signal is still present at the mother's abdomen. Either M1 gets amplitude gets reduced and delayed when we detect at the abdomen, but the PFN is a very strong source of interference when we are trying to determine the fetal ECG. So the key idea here is to remove this PFN by using the adaptive filtering concept and retain FFN as much as possible and retain the fetal ECG as much as possible. Okay, so with this configuration, it has become pretty easy now to think about that. And the filter that we are trying to design is an adaptive filter. So that's why the coefficients of the adaptive filter, W, is what we need to determine in a steady state when the filter is converged or the approach of optimization has reached its point of optimality. Okay, when that's happening, then the output of this linear filter would be an estimate of the mother's ECG at the abdomen, then by subtraction of that, the output that we get from this adaptive system is an estimate of the fetal ECG. Okay, so it's estimate of fetal ECG. You see, I'm using the word estimate because it's pretty much impossible to get an accurate estimate of the fetal ECG for many reasons. So that's why we put an estimate, and we hope the estimate is as close as to the ground truth ECG F1. Okay, so it's an estimate of fetal ECG. So that's the intention here. So when we design the system with the two inputs getting into the adaptive filter, M1 and AN, the output coming as fetal ECG F1 estimate. There you go. Now you can estimate the heart rate of the fetal. And as we all know, it's so important in monitoring during labor and delivery, and also during the different stages of pregnancy to find out how the baby is doing. Okay, so we have done this thing, and just to recap, M1 is the mother's ECG, AN is a signal recorded at the abdomen of the pregnant mom, F1 is a fetal ECG estimate, and the P hat N is the estimate of the mother's ECG present in the abdomen. Okay. Now, very, very important thing for this filter to work in an optimal way is the mother's ECG and the fetal ECG are assumed to be uncorrelated. Okay. That's very key assumption. Okay. Mother's ECG and fetal ECG are uncorrelated. It happens naturally, they're uncorrelated. Okay. Because of the very difference in heart rate, okay, between mother and fetal heart rates, naturally it tends to be quite different. So it's possible to separate. Okay, so that's a key step here. Is this assumption of uncorrelation? If there is some correlation, it's still okay, and that's where we get an estimate which may not be fully accurate, but we get the best information possible with whatever is happening between the real world scenario of fetal and mother's ECG. Now we can go back and look into the various concepts that we found in terms of designing the filter. When we go through this whole aspect of the least mean squares technique and the RW is equal to P technique, because of this assumption of uncorrelated between the fetal ECG and the mother's ECG, it happens that we could implement RW equal to P, but we know practically it might be a large filter order. Here, the filter order in a fetal ECG tends to be very high. I mean, I'm talking about order of 7 and higher, you know, so number of coefficients W you need is 7 or higher. Now you might wonder, is there a theory that determines what should be the order of those adaptive filters? We will see that later. Okay, there is some indications and some theory that could support in selecting a right order of the filter, but for the time being, we know in an application like this, the order tends to be pretty high. Okay, so we have to obviously depend on algorithm like least mean squares in finding out the filter coefficients W. Okay, so it happens this uncorrelated assumption that we just talked about between fetal and mother's ECG is ensuring that your F1 and Pn are uncorrelated. F1 and Pn are uncorrelated, and Pn, okay, I'm putting the word uncorrelated. Okay, it means the cross correlation between them is so low, or it could be even zero if it's in an ideal world. And it happens the Pn, which is determined at the mother's abdomen and the mother's chest ECG. So your Mn and Pm are correlated. It's true because it's coming from the same heartbeat. Okay, mom's heartbeat detected at two different sources, but they are correlated. Okay, again, we don't expect a 100% correlation between Mn and Pn, because by the time we sense the ECG at the mother's abdomen, as indicated, the signal amplitude gets probably attenuated, reduced, and also there would be slight delay between the real heartbeat and the point when we detect at the mother's abdomen. There would be a delay. Okay, so nevertheless, when you do the cross correlation between Mn and Pn, you will typically get a higher value to that. Okay, so that's assumptions. Okay, that is that these two things are correlated, and these two things are uncorrelated. Because of that, what happens is that when the filter is going through the update process through the LMS technique, okay, the filter coefficients are updated through the LMS technique. When the filter converges, in other words, when you don't see a difference in the output, that means the filter is converged. It happens that because your MN and Fn also uncorrelated, Mn and Fn uncorrelated, the output of this adaptive filter is P hat n, because the P hat n is coming out as the output of this filter, linear filter, adaptive filter. Now, by just in the next stage during this process, it happens that we have an estimate of Pn, it's subtracted, and all we have is f of n, okay, f of n that's coming out. Okay, so this is after the filter is converged. Before it has converged, you will be getting also some output that is coming out here, and essentially you will see that there are some values of Fn are biased because the filter hasn't reached the point of convergence. Now, how do we make the filter convergence? We know the LMS has a few key steps involved. If you want a faster convergence for the LMS, you can select a step size mu to be a large value. It will make sure that you reach the convergence very fast, like if you want a rapid estimate of the heart rate, but we might run into the risk of missing the optimality point. Then your filter may not reach that optimal point and it might struggle to do any convergence. On the other hand, a small mu will guarantee you convergence, but again, it takes time. So it's always a balance between the right mu that needs to be selected. And just like how we saw, there are various variations of least mean square algorithm that could also be implemented to find out your W. Okay, so that's essentially a very important and a practical application of using least mean squares for estimating adaptive filter coefficients. In this case, it happens to be fetal ECG estimate, subsequently followed by fetal heart rate estimate, which, you know, once we have the ECG, we can go through the various procedures like the Pan-Tompkins and get the heart rate, and you can even measure the heart rate variability, which might also give you an idea about the psychological conditions of the baby. Okay, so not necessarily the heart conditions, also the heart rate variability, as it's been known as quite a bit of connection to the autonomic nervous system. So you can get other variables as well. So this same logic, which we talked about mother and fetal ECG, could be translated into other areas of biomedical signals. We know EEG has an interference with EOG. Then we also know your heart sounds called phonocardiograph. PCG has some overlap with the respiratory sounds or lung sounds. So if you want to either determine lung sounds, your PCG, the phonocardiogram, is an artifact. Or if you want to determine heart sounds, normally lung sounds act as an interference because both the organs are almost overlapping and nearby to each other. So that's expected. The other sources is that, for example, if you want to detect the vibration signal from the knee, which we call as vibroorthogram, VAG, then your muscle signal from close to the knee, which is the rectus femoris muscle, for example, acts as an interference. So in the context of vibroorthogram, vibromyogram coming from the leg would act as an interference. So you can keep building these examples. There are many such examples which we normally see in recording these signals. Okay. Now, when we're doing this thing, similar to what we have seen with adaptive filter, if you make sure the inputs are configured properly, okay, all you have to do is that you have to ensure that the inputs are configured, inputs are properly given to the filter, and you need to select the right filter order, so that you know how many Ws you need. Normally, it's good to go with higher order if you feel your signal is not noisy, but a lower order might do an under modeling. So that's what you need to keep in mind. And we will come to the point of determining optimal model order towards the end of this topic. So input should be properly configured, right filter order, and obviously the right algorithm, such as the least mean squares, right, could be selected to determine the adaptive filter coefficients, right algorithm such as LMS. There are various variations of LMS, and there is also some faster techniques compared to LMS, which we are not going to cover in the course. It's called RLS, recursive least squares technique. Okay, RLS is similar to LMS, and in many applications it is much faster convergence. Definitely it's a little bit more complicated than LMS in terms of the algorithmic description, but that's also very highly used in adaptive filtering applications. Okay, but we won't be looking into the details of RLS in this course. So this gives a very good idea to deal with various types of noise and interferences. There is also no harm in using a similar adaptive filtering configuration even to remove white noise. Simple reason is that white noise is uncorrelated with the signal of interest, and you could use the same logic we saw in the example, in the numerical example that we just did, to remove even white noise. Okay, but nevertheless, we also know how to remove white noise through other approaches like synchronized averaging, moving average, to some extent using bandpass and low-pass filtering. Okay. So with that application, we will switch to a second key application of using adaptive filters. And in the specific example, I will be taking LMS as an algorithmic solution for that. Adaptive segmentation is super important these days, okay, because we are monitoring signals on a longer duration. Continuous monitoring is currently happening with all these smart wearable devices, watches, phones, your Fitbit type wearable devices. So you need to find a way to analyze those signals. And typically what people do is that if you get, let's say, a 3-hour data, for example, you're monitoring somebody on a continuous basis for 3 hours, let's say 3 hours of ECG data, then you have this ECG data which is going for 3 hours, and we all know that's a pretty huge time series signal to handle. We cannot process this with many of the tools, the whole signal, which is 3 hours duration. So normally what we do is that we simply segment the signal into fixed windows. Like, okay, we select, for example, a 30-second duration, or in some cases a minute, or in some cases even 5-minute duration, and we truncate the signal into those short segments, chunks, and we process them. So we also called this as windowing process. So it's, in other words, fixed segmentation using fixed windows. And we are all familiar with various windows that could be used, like Hamming, Hanning, Blackman, Kaiser. There are many windows, fixed windows that could be used. And we have also seen how windowing could be used even in truncating an IIR filter coefficients to give an FIR filter coefficients. Okay, so a typical approach people use is, if you have a longer time domain signal, if you want to do the analysis, people break the signal into shorter chunks by using fixed window. Okay, and this has been a very common practice, even most commonly in speech processing. Speech processing, they realized that not much of your vocal characteristics change within a 25 millisecond duration. So what they do is that they break a given speech signal into 25 milliseconds chunks, okay, typically. And now if we know the sampling frequency, then you know the 25 millisecond will correspond to whatever the sampling frequency is given. You have to just multiply with that. And those are the time samples that you need to work, for example, in MATLAB. So that's a very simple, plain, straightforward fixed segmentation approach. Okay, it's possible that in a biomedical signal where maybe the characteristics of the signal are not changing rapidly, for example, either in sleep or even in longer term ECG monitoring, there may not be a lot of events of interest happening on a very frequent basis. So the fixed segmentation, you're basically doing overdoing the task. You're doing an over segmentation and getting more resources involved there. And that's where we could probably get away with that by just using a smarter way of an adaptive segmentation process. In other words, just splitting the signal or dividing the signal wherever there is an event of interest. Okay, and this adaptive segmentation is very commonly used, as I indicated, in a lot of longer-term variable-based signal processing applications. Okay, now how we could do that? Nothing. Again, by just using LMS algorithm. We have been talking about the filter is converged. The filter is converged is that where your filter coefficients have reached some form of optimality in a least mean squares algorithm. It means your error function, if you plot the error function E square n, which is error function, or it's also connected to the objective function. In the beginning, the error is huge because there's a huge variation between the desired response and the output that's coming out of the filter or the estimate. So the error is high. As time goes by, the error decreases. Okay, that's what we get in a typical least mean squares implementation. And this curve, the plot of the E square n versus n, is also known as a learning curve. Okay, it's also a concept very popular in machine learning. Okay, learning curve. It shows that with respect to the number of time samples, how fast your algorithm is learning. Okay, so the red plot I plotted may be something that's for a specific mu in the case of least mean square, because least mean square, the main part is the mu, the step size. And I might also have the filter take a while to converge to that point, like the green line. Okay, the main difference here is that both the techniques, the green line and the red line, have used LMS algorithm. The only thing is difference is that in this case, it happens that the mu for the green is pretty large. Okay, because obviously a smaller step size, so it takes a while to converge to the steady state value. The steady state value is here. Okay, whereas in the red one, the mu is higher in the red one, and the mu is smaller in the green one. Okay, smaller step size takes longer time, larger step size takes faster time. Okay, so the mu is higher with the red line, and the mu is smaller with the green line. So this is a simple example with the least mean squares technique that we saw. Okay, so nevertheless, it converges to this point of optimality. Either you use a larger, smaller mu. This is a point where it converges, so it doesn't go below that. Okay. And normally this area where it doesn't converge all the time to zero, if it converges to zero, it's great. It converges to very small value. It's because of the residual noise present in the signal. Okay, and to some extent, this black area could also be used to estimate the variance of the noise. Okay, so I'm not going to go into the details, just to point out that if you design the right adaptive filters, it will converge to a value, and there is no further decrease from that value. And we tell at that point the filter is converged. And typically it happens to be a very small value. In an ideal case, it should be zero. Okay, so that's a learning curve that happens in a typical adaptive filter, and W optimal is estimated when this has reached that black area. Okay, now this is all true when if you go back into LMS connection with the concept of RW equal to P, it all happens when W optimal is R inverse P, mathematically speaking. So it has reached the optimal point and R inverse P is equal to done. But in a process where your R matrix is changing with time, okay, if your R matrix is changing with time, so for a given signal, R matrix is assumed to be stable, that the matrix values are stable. But if that R matrices values are starting to change with time, or R becomes a function of time, we call that process as a non-stationary. Okay. So pretty much all biomedical signals we have, when you take the signal for a longer duration, it goes through the process of non-stationarity. Non-stationarity is a statistical behavior of any biomedical signal in which the mean and the variance are changing with time. Okay, and you can imagine in a sleep signal, if you do the autocorrelation matrix, speaking in a high level, that autocorrelation matrix would change for the different sleep stages. Okay, so we cannot tell that entire sleep signal has one autocorrelation matrix. It will change over time. And that's possible because the moment we are starting to monitor a longer term signal, you enter into non-stationarity, which essentially indicates your R matrix is changing with time, which also indicates that your W value you're getting also becomes a function of time. So it's no one optimality. When that W becomes a function of time, it's nothing but your learning curve, which we saw before, is starting to converge and it's starting to diverge again when that non-stationary point is reached. So this is an example of the same learning curve. It's another y-axis J again, or E square N plot, and x-axis is N. So same thing I showed you. Here I'm showing this is for a non-stationary signal, which is typically with all longer term biomedical signals, it's non-stationary. It happens your filter as going through this process. Let's assume we selected a good mu. Yes, it has converged. Then suddenly again, it's starting to diverge. Your error is starting to pick up and starting to converge again. Whenever that error is starting to pick up means that particular point, the signal properties have changed, okay? So for example, the sleep one, maybe I'm going from sleep stage 1 to sleep stage 2, the signal error function picks up again and it reaches steady state. And again, I have the second boundary. Then again, it starts to decrease and pick up again. So this process can continue on wherever there are points of non-stationarity. Okay, so this is super important because, in other words, this is some sort of an unsupervised machine learning where this adaptive filter, the weight vector or the error square function, is helping us to determine where your physiological process is changing in a longer term observation. This could also mean, we took the example of a 3-hour long ECG, this autocorrelation function might change wherever a person is showing a drastic change in the heart rate, okay? Heart rate and heart rate variability. So this is where it comes very handy that we don't have to worry about following a fixed segmentation where we take fixed windows and break the signal into smaller chunks. And you can imagine, I mean, going back into your basic signals and system concept, if your window length is short, like a small window duration, then obviously your estimate of the frequency would be very approximate, okay, because of Fourier concept. Anything that's for a shorter duration in time will have a more spread in the frequency domain and vice versa, okay? So a shorter time window will give a very poor resolution, whereas a longer time window will give a better frequency resolution. Because for Fourier, the best estimate of any frequency is when the signal is observed from -infinity to +infinity. Longer the observation of a signal, better the frequency estimate. But we also have a problem when you observe the signal for a longer duration, you might be introducing non-stationarity and you might not be getting the local variations, the dynamical variations of the signal, okay? So this is similar to telling, for example, today, if I tell you the maximum temperature is going to be 5 degrees centigrade, and the minimum temperature is -1 degree centigrade, okay? So that's what you get a global information. You know, okay, it's going to be cold, that we are going to end up in -1 degree centigrade, and the maximum would be 5 degrees centigrade. But this is like giving you the global information and lacks any local specifics like non-stationary information. On the other hand, if I tell you in the morning time frame, the temperature would be 5 degrees centigrade. In the evening, from 6 p.m. to 10 p.m., it's going to be -1 degree centigrade. Now you have a better idea about the local information that, okay, in the evening, it's going to be -1 degree centigrade, and you can dress appropriately, okay? That's a huge difference here, okay? So far, any analysis we have been doing, when we take this global information, that when you take a longer time window and do an estimate, it's by all means giving the global parameters, okay? Like what would be the maximum minimum temperature in a given day. But when I break the signal into smaller chunks, I get a better local estimates. And that's exactly we're talking from a signal processing concept, how we break those smaller chunks, either in an adaptive way or a fixed way. Fixed way is okay, but it might lead up in giving more segments than needed. We don't have to worry about that. Whereas if you use an adaptive segment for the same toy example that I showed you, it shows that adaptive segment boundaries are only at these points. How did I determine these adaptive segment boundaries? By using techniques like least mean squares and monitoring the least mean squares error function, we got those. Through this approach, you could see that rather than having 1, 2, 3, 4 segments, I'm just having one segment determining the same process. Okay, so I don't have to waste those additional resources, and I don't have to do a frequent analysis in those smaller chunks. It basically tells this chunk, this and segment are pretty much the same behavior or statistical characteristics. This is so important that it really synchronizes very well with a lot of the biomedical concepts that we see, because in many biomedical signals, especially when we are monitoring patients with non-emergency conditions, like in a non-ICU setup, you will see the physiological variables changing over time, but they change over a longer time. They don't change every second, or they don't change every minute. Some might change on an hourly basis. Most of them change on a daily basis. So it becomes so important what kind of segmentation process we need to use, and this adaptive segmentation comes in so handy. So it's basically an offshoot. Adaptive segmentation is basically an offshoot of the adaptive filtering techniques like LMS in this specific example, where in LMS we have the flexibility to monitor the error function E of n. All I'm doing is monitoring the error square function, and we know the error square function, if the process is stationary, it should remain stable for some time. The moment there is a non-stationary point, it will start to shoot up again and come back down and shoot. So you can see this particular graph will give you, okay, there are at least 2 points of non-stationarity, and all you need to do in the signal is to segment your boundaries according to this time information, and you don't have to really worry about segmenting them very often. Okay, so that's basically in a nutshell the process of adaptive segmentation, and it's a fantastic tracking of your signal behavior as well. Okay, and also gives an idea about the degree of non-stationarity of a signal. For example, if the same thing, if I had a process like that where the adaptive segment boundaries were changing very often, it indicates to me the black signal is essentially varying very dynamically and is showing a highly non-stationary characteristics. So physiological signals, even from a higher level, we can understand like ECG tends to be non-stationary, but it's not as non-stationary as a dynamical signal like an EEG, for example. Okay, speech is controlled by the humans. It depends what we speak. If we take a concert type music, there are various musical instruments, there is various vocal inputs, so it is possible that the concert audio signal might be very non-stationary compared to a solo performance, okay, or for that matter a conference talk, you know, where only one person is speaking. So there you go. It kind of determines the complexity of the given situation, and it happens that particular complexity, we do have a statistical description of that complexity called a non-stationarity. Okay, so I won't be getting into other forms of non-stationary techniques available out there, which does this kind of a segmentation pretty automatically, and such algorithms are widely available and quite popular, easy to implement as well, but it's not within the scope of this particular course. Just to give you some other example of non-stationary techniques is that there is something called wavelet filtering or wavelet techniques. Wavelets are similar to what I described before. They have an inbuilt way of doing adaptive segment, and they're considered to be a pretty advanced version of doing a short-time Fourier transform. Fourier transform, as I indicated before, if you want to apply on a non-stationary concept, you have to break those non-stationary into smaller windows. Within those stationary segments, we can apply a Fourier transform, because Fourier transform essentially works well only when you have stationary segments. Then that is nothing but short-time Fourier transform, and the squared value of the short-time Fourier transform coefficients, it gives energy distribution of the signal in a plane called time frequency plane, and that's something called spectrogram. Okay, so spectrogram, which is based on short time Fourier transform, along with wavelet and its equivalent, what's called scaleogram, are very popular means of non-stationary analysis. There are recent variations to these both the techniques, which are also based on entirely data-driven approach, and that's called empirical mode decomposition, EMD, empirical mode decomposition. So in a nutshell, there are many non-stationary approaches that we could do. In this course, we will just see how to deal with it through using adaptive segments and least mean square technique. But as I said, you can expand that and look into other advanced concepts like wavelets, short time Fourier transform, and EMD, empirical mode decomposition techniques. My lab does extensive work in non-stationary segment processing. So most of the master's and PhD thesis develop these advanced forms of non-stationary for both processing as well as for machine learning applications. So with this, we would stop here, and we will come back and look into another variation of what we just saw. And it was developed pretty independently, but it could be easily connected to what we just saw in terms of adaptive filters, and also back into the classical filter we have seen before, such as pole zero configuration. And that topic is called prediction, linear prediction, very interesting topic. And we will come back and discuss how we could make the digital systems or the filters do prediction for us. Thank you.